Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the heartbeat of civilization. In this page, we will cover the concept of time series data and how it acts as the invisible pulse of our modern world. There is a heartbeat underneath the noise of civilization. It pulses through power grids, microsecond stock exchanges, and seasonal supply chains. Time series data is the most informative and treacherous data science has ever attempted to master. It represents the chronological recording of events, capturing the rhythm of human activity and natural phenomena. When we look at power grids, we see the ebb and flow of electricity demand as cities wake up and go to sleep. In stock exchanges, we see the frantic oscillations of value happening in the blink of an eye. In supply chains, we observe the slow, seasonal waves of production and consumption. Mastering this data is not just about statistics. It is about understanding the very fabric of how our society functions over time. Every data point tells a story of a moment past, and when joined together, they form the melody of our collective existence. However, the sheer volume and complexity of this noise make it a monumental challenge for researchers and analysts to truly decipher the signal from the static. In this slide, we explore the profound concept of the butterfly effect and the birth of chaos theory. In 1963, a meteorologist named Edward Lorenz discovered that complex systems amplify tiny perturbations. He found that a rounding error of less than 1 part in 1,000 diverges into an entirely different future. This realization changed everything we thought we knew about prediction. Chaos theory tells us that the past is not a perfectly reliable guide to the future, because a single vibration can eventually create a hurricane. Look at the visualization of the Lorentz attractor on the screen. Those swirling loops represent the boundaries of possibility, yet the exact path within them is highly sensitive to starting conditions. When Lorentz entered 0.506 instead of the full decimal, the entire weather simulation changed course. This teaches us that in high-dimensional systems, precision is both our greatest tool and our greatest limitation. We must respect the fact that small changes today can lead to massive deviations tomorrow. This inherent instability in complex systems is why long-term forecasting remains one of the most difficult problems in modern science. It reminds us that, while we can map the patterns of chaos, we can never truly tame its unpredictable nature. The human limitation is a critical factor when we discuss data science and forecasting. Human cognition evolved for short-term pattern recognition, which served us well when we were avoiding predators or gathering food. However, in the modern era, we struggle to process how 50 interacting variables influence each other across years. Our brains are naturally wired for linear time and short horizons. We look at the world through a narrow lens, often missing the broader context of complex systems. As shown in the illustration, the goal of modern predictive modeling is no longer just guessing what happens next. Instead, it is mapping the probability cloud of the future. We are moving away from the simplistic human approach of predicting a single event and toward a more sophisticated mathematical approach. This requires us to recognize our biological shortcomings and build tools that can see what we cannot. We need systems that can track dozens of simultaneous variables and understand their non-linear relationships over vast periods. By acknowledging that our intuition is limited to the immediate and the obvious, we can begin to appreciate the necessity of advanced algorithms that broaden our perspective and allow us to visualize the many possible futures that lie ahead of us. As we move into the technical evolution of forecasting, we encounter mathematical decay and the vanishing gradient. Early sequence models attempted to predict the future by remembering the past through a loop mechanism. However, they faced a fundamental problem. The learning signal travels backward through time and exponentially decays. This is often called the math of forgetting. Imagine multiplying a fraction by itself 1,000 times. Very quickly, that value reduces to 0. By the time a model reaches day 1,000, the memory of what happened on day 1 has mathematically ceased to exist. This creates a horizon beyond which the model is essentially blind. It cannot connect current events to historical precedents that occurred long ago. This decay is visible in the wave pattern on the screen, where the vibrations grow smaller and smaller until they vanish into a flat line. For years, This was a massive wall in the field of artificial intelligence. It prevented models from understanding long-term dependencies, such as how a policy change 5 years ago might affect a market today. Solving this required a complete rethink of how neural networks store and retrieve information over long sequences, leading to the development of more robust architectures that could maintain a signal across the vastness of time. The next step in evolution was the introduction of LSTMs, but they brought their own issues, specifically the bottleneck of the sliding window. LSTMs fixed mathematical decay by using memory cells, but they introduced a structural bottleneck. They process time sequentially, forcing massive historical context into a compressed and often impoverished vector. This means the model can become blind to the big picture. For example, an LSTM might miss exact patterns from exactly 365 steps ago, such as the specific behavior of consumers during last Christmas. Additionally, these models can become overwhelmed by simultaneous detail within their current focus area. The sliding window acts like a narrow spotlight moving across a long, dark hallway. It can see what is right in front of it, but it loses the context of where the hallway started and where it is going. The chaotic visual in the center of the slide represents how information becomes jumbled and messy when forced through this narrow sequential process. While LSTMs were a significant improvement over earlier models, they still lack the ability to truly see the entire timeline at once. They were still trapped in a sequential mindset, unable to jump across time to find the most relevant pieces of information for the current prediction task. Now we enter the realm of engineering omniscience with the Temporal Fusion Transformer, or TFT. The TFT refuses to flatten data into a simple stream. Instead, it structurally separates permanent facts from chaotic fluctuations, leaping from sequential reading to simultaneous vision. This architecture is designed to handle the complexity of the real world by using specialized components. At the start, we have the gatekeepers which decide what information is allowed to enter the system. From there, the data flows into 3 distinct paths. The temporal telescope allows the model to look across different scales of time. The identity layer ensures that the model maintains a sense of the specific entity it is predicting. Finally, the adaptive depth layer allows the network to choose how much computational power to apply to a specific problem. This represents a paradigm shift in how we build AI for time series. Rather than treating all data points the same way, the TFT treats time as a multidimensional landscape. It can zoom in on recent volatility while simultaneously keeping an eye on long-term trends. This structural sophistication allows the model to remain accurate even when faced with the kind of chaos that would cause simpler models to fail. It is an engineering masterpiece that reflects our best understanding of temporal dynamics. A key component of the TFT is the variable selection network, which helps the system filter the noise. In the real world, most data is noise. If you force a network to process everything with equal weight, it will quickly become confused and inaccurate. Instead of this brute force approach, specialized subnetworks evaluate every variable at every microsecond. This is what we call a soft ranking. The system dynamically decides which variables actually matter right now. For instance, in one moment, the price of a commodity might be the most important factor. In another moment, the day of the week or recent sales trends might take precedence. As you can see in the diagram, dozens of potential data inputs are funneled through the VSN. Only the most relevant signals are allowed to pass through at full strength, while the noise is dampened. This mimics the way human experts focus on key indicators while ignoring distractions. By using this dynamic selection process, the model becomes much more efficient and robust. It does not waste energy on irrelevant data, allowing it to maintain a clear vision of the factors that truly drive the future. This ability to prioritize information in real time is what makes the Temporal Fusion Transformer so effective at handling high-dimensional and messy datasets. Static covariate encoders are essential for establishing identity within a predictive model. Unlike older models like LSTMs, the TFT separates things that never change from things that always change. This concept is referred to as identity before action. It gives the AI a distinct sense of who it is before it looks at what is happening. Think of the static DNA as the unchanging characteristics of a system, like the location of a store or the fundamental properties of a physical object. The dynamic pulse represents the constantly fluctuating environment, such as weather or market prices. By separating these two, the model avoids the need to derive context at every single step. It already knows the foundational facts, so it can focus its attention on interpreting the new incoming data. On the slide, you can see the solid black blocks representing the static identity, providing a stable foundation for the orange waves of the dynamic pulse. This separation makes the learning process much more stable. The model does not get confused between temporary spikes and permanent traits. It provides a level of consistency that is vital for long-term forecasting, ensuring that the predictions remain grounded in the reality of the specific entity being studied. It is about understanding the fixed background before trying to predict the moving foreground. Adaptive depth via gated residual networks is another brilliant feature of modern time series architecture. The fundamental realization here is that not all patterns require equal computation. Some things are simple and obvious, while others are complex and chaotic. The gated residual network, or GRN, acts as an adaptive brain for the model. For simple patterns, the system can use a shortcut that bypasses complex logic, saving time and energy. However, during chaotic moments, the GRN engages its full non-linear computational power to solve the problem. This is shown in the diagram where a green arrow represents the simple path and the orange path represents the deep, complex processing required for difficult signals. This flexibility allows the model to be both fast and deep. It does not overthink the easy parts, but it has the capacity to handle extreme volatility when it arises. This mimics the way humans can perform routine tasks automatically while dedicating intense focus to new or difficult challenges. By using these gates, the network can effectively manage its internal resources, ensuring that the most complex math is reserved for the most complex data. This results in a model that is not only more accurate, but also more efficient in how it uses its underlying hardware. It is a smart way to balance depth and simplicity. We must also address the flaw of the point forecast, which is a major issue in traditional AI. Most AI systems output a single number, such as predicting that the price will be exactly $100. This approach is dangerous because it strips away nuance and makes risk management impossible. A single future presented as absolute certainty is an epistemic failure. The world is full of uncertainty, and a single number cannot capture the range of possible outcomes. As you can see in the scatter plot, the data is often messy and spread out. A single line through the middle is often wrong and fails to show the volatility of the situation. When decision makers rely on these single-point forecasts, they are often blindsided by events that the model failed to account for. We need to move toward a more honest form of forecasting that embraces uncertainty rather than hiding it. If we only see one path, we are not prepared for the dozens of other things that could happen. This realization has led to the development of probabilistic models that provide a range of outcomes. By understanding the spread of the data, we can make better decisions that account for both the most likely scenario and the potential for extreme outliers. It is a shift from false certainty to calculated probability. Predicting the probability cloud is how the TFT solves the problem of point forecasts. Instead of saying yes or no, the TFT predicts maybe. It generates a calibrated probability distribution, which is essentially a spread of uncertainty. This is achieved through a technique called quantile regression. It is driven by an asymmetrical pinball loss function that penalizes under-predictions and over-predictions differently. This allows the model to map the full spectrum of risk. On the slide, you can see how the forecast expands over time, creating a shaded area of potential outcomes. The dark center line represents the median, but the surrounding layers show the varying levels of confidence. This is incredibly useful for real-world applications. For example, a retailer might want to know not just the average expected sales, but also the worst-case scenario to ensure they have enough stock. By providing a cloud instead of a line, the AI gives us a much more realistic view of the future. It acknowledges that as we look further ahead, our certainty naturally decreases. This transparent approach to uncertainty allows human operators to make more informed decisions based on their specific risk tolerance. It transforms the AI from a simple calculator into a sophisticated tool for strategic planning and risk mitigation. One of the most powerful features of the TFT is its simultaneous multi-horizon vision. This is made possible by interpretable multi-head self-attention. This mechanism allows the model to look across the entire timeline simultaneously, rather than one step at a time. The diagram shows direct connections between different points in time, such as December 2023 and December 2024. These connections allow the model to identify seasonal patterns and sudden shocks without waiting for a signal to slowly travel through sequential memory. It can instantly see the relationship between what happened a year ago and what is happening now. This is a massive advantage for forecasting things like holiday sales or annual weather patterns. The attention heads act like multiple sets of eyes, each looking for different types of relationships across the timeline. One might focus on short-term trends, while another looks for long-term cycles. Because this process is interpretable, we can actually see which past events the model is using to make its current prediction. This removes the black box nature of traditional neural networks and gives us insight into the model's logic. It provides a global perspective that was simply impossible with older sequential architectures. By seeing the whole story at once, the model can make much more accurate and contextually aware predictions about where the story goes next. The Cassandra paradox introduces a fascinating philosophical challenge in the world of prediction. If the AI perfectly predicts a market crash and we act to prevent it, the AI was technically wrong because it was right. This is known as reflexivity. A forecast accurate enough to act upon is powerful enough to change the outcome it predicted. The cycle on the screen shows how an accurate prediction leads to human intervention, which creates an altered reality, finally resulting in a falsified prediction. This creates a strange loop where the better our models become, the more they change the world they are trying to predict. This is especially true in social and economic systems where human agency is a major factor. If everyone believes a certain stock will rise, their collective action will make it happen. But if a model predicts a disaster, our efforts to avoid it will make the model appear inaccurate. This paradox reminds us that we are not just passive observers of the future. We are active participants. Our predictive tools are now part of the feedback loop of civilization. We must learn to use these tools with the understanding that they are not just showing us a fixed destination, but are helping us navigate and shape the path we are on. The goal is not just to be right, but to be useful in guiding us toward better outcomes. As predictive systems become more integrated into our lives, we risk falling into the deterministic trap. As these systems become embedded in institutional decision-making, the range of surprising futures narrows. This leads to what we call the loss of agency. If the future is pre-calculated by an algorithm, is it still the future, or is it just the output? When banks, governments, and corporations all use the same models to make decisions, their actions begin to converge. This creates a more predictable world, but also a more rigid one. The illustration shows a long line of people walking along a predetermined grid, representing the loss of spontaneity and individual choice. If every risk is calculated and every trend is anticipated, there is less room for the unexpected or the revolutionary. We might find ourselves living in a world that is optimized for efficiency, but drained of its creative potential. This deterministic path can lead to a self-fulfilling prophecy where we only see the futures that our models are capable of imagining. We must be careful not to let our tools become our masters. While prediction is a powerful ally, we must preserve the human element of surprise and the ability to choose a path that the data could never have anticipated. The future should be something we create, not just something we compute. Finally, we arrive at the cartography of time. We are no longer just predicting the future. We are fusing every moment that ever was into a single, understandable map. This turns surprise into an engineering failure. By using advanced tools like the Temporal Fusion Transformer, we are building a three-dimensional landscape of probability and history. As you can see in the final visualization, the chaotic loops of the butterfly effect are now contained within a structured grid. We are mapping the boundaries of the unknown. However, this level of clarity brings a deep question. Once we can see the end of the story, will we still want to play the game? If we achieve a state where every major event is anticipated and every risk is mitigated, what happens to the human experience of discovery and hope? This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.